matrix on the board last time, which I was not yet done with. So we have this matrix, which I will try to recopy. You guys can correct me if I screw it up. -1, 1, 3, 2, -5, and we actually reduced it to echelon form. And we had kept track of the constraint ideas with the B's so that we actually had an E matrix that told us that E times my original A was this matrix in echelon form. And if my notes are correct, it should have been like this. Huh, is that what it was?
Yeah.
3, 1, -5, and then -4, 5, 1. So we had this matrix times A is the echelon form. Is that agreeing with what you have? And then we went the last step to the reduced echelon form, because then we could read off the general solution in standard form. That would be good if I did it correctly.
-1.
So this was the reduced echelon form. Okay.
I think it's a +2 in the top right.
Yeah.
Is there a problem?
It's a 2 on the upper right.
Oh, yeah, it's.
Oh, yeah, it is. My notes are wrong. See, never trust notes.
We're in trouble.
So, okay, so we had a discussion of row space, column space, null space, left null space, and we had bases for all of them, but I wanted to actually finish up that discussion today a little bit. So, what did we say in general? If you have a matrix, how do you get a basis for the null space?
General solution.
You take the vectors that come up in the general solution of AX equals 0, and we argued why those would span and would always be linearly independent. What about the row space? Non-zero rows of any echelon form. Column space was the interesting one of the interesting ones. Look at the pivots in your echelon form. You go back to the original columns. And we did explain why those were linearly independent. Because if you deleted all the remaining columns and just reduced echelon form, you'd have a matrix with just these two columns here. And there's obviously two pivots in two columns. So the only linear combination of the columns of this matrix that gives you 0 is the trivial one, which means the only combination of the columns of this matrix, which gives you 0, is the trivial one. And then we also said that you can see how to write any of the remaining columns as a linear combination of these by using the basis vectors for the null space. Because the basis vectors for the null space, remember, told you that, for example, your original matrix times this vector was 0. Well, that means first column plus second column is 0. So the second column is the negative of the first. Hey, it is. Amazing.
Huh.
We also had, for example, this vector. Well, multiplying the matrix times this vector should tell you that negative this column plus negative this column plus this column is 0. In other words, this column is the sum of those two columns. Uh-oh.
No, it is.
Yeah.
It is.
Oh, it is. And lastly, I shouldn't press my luck here. lastly, that basis vector for the null space should tell me that the last column is twice the first column minus the third. All right, so you guys understand this so far. The one we ended with in a great rush was the null space of the transpose. Now, some people like to teach this material and just say, take the matrix, transpose it, and do the same algorithms and find the null space. You can do that, but why do all that work when we already have the information here? So, remember, we're saying vectors in the null space of A are vectors that express what linear combinations of the columns of A give you 0. So vectors, remember, in the null space of A transpose if you have a vector that satisfies this, then if I transpose that equation, I can think of it this way, which is why it's called the left null space, because it's null from the other side. But now when you look at it, it's saying what vectors multiplied on the left by A give me 0. So that's doing what linear combinations of the rows. And I'm claiming that that's exactly what these tell you. Because, look, this says if you multiply E by A, you get this guy. So in particular, if you take the bottom rows here and multiply by A, you get the rows of zeros in the echelon form. So that's saying that 3 times the first row plus 1 times the second row minus 5 times the third row plus 0 times the fourth row is 0. Where did we get these from? We got them from the B's. Well, when we had our equations with the B's, they were coming by saying, when we did those appropriate combinations of the rows, we got this, namely 0. Check it out. What's 3 of these plus this minus 5 of these? 3 of these plus this
0.
minus 5 of that. 3 of it, well, okay, we don't need to do. 3 of this, 5, plus this.
Wait, did you say 5?
Yeah, no, that's
6.
6
minus 1.
I add instead of multiplying. Don't ever do that. 3 of this is 6, plus this subtracts 1 is 5,
Plus this is
minus 5 is 0, etc. So these rows came from what constraints have to hold for the system of equations to be consistent, but it's also telling you combinations of the rows. So the bottom, so the claim is that the rows of zeros, so the coefficients of the constraint equations, which is give the rows of E corresponding to rows of zeros in the echelon form. So what is not perhaps obvious, that we'll follow in a minute, is that these vectors span, namely the only linear combinations of the rows that give you 0 are combinations of these two vectors. That's perhaps not obvious. And what's also perhaps not obvious is that these vectors are linearly independent. The bottom rows of E give a basis. Well, you actually can tell me why these two vectors are linearly independent, looking at this example.
You just add 1 to 0, that third column will be 0.
No, but can you, what argument is not going to depend on the specific numbers, but more on the algorithm? What do you notice in these columns?
Yeah.
Pivots.
Yeah. Column
right? There's 1 here and 0 here, 0 here, 1 here. That means these vectors are linearly dependent,
Right.
right? Okay. So, again, it's not totally obvious why they have to span, except if you had another relation among the rows that was not a linear combination of these, that would have to say that you had some combination of these rows that gave you 0. That wasn't the trivial combination. But we know these are linearly dependent. So there can't be any other relations other than the ones that are fiddling with these zeros that are already here. That's basically a proof, but you'll have another proof from what we do. Okay, so that's as much of a proof of the theorem as I'm going to give. If you want to look at the book, it has proof with abstract notation in it. But my view is if you actually understand the explanations we've done with the concrete example, you understand it. And this is certainly not a proof I would expect you to write out in abstraction. But I do want to make some comments here and give you some applications of this stuff. What's our definition of the column space? No. Definition of the column space.
It's a span
Span
of the
Pivot
column.
column.
On the column vectors.
of the column vectors. So all vectors that can be written as linear combinations of the columns. Does that have something to do with consistency?
Yeah.
What does it have to do with consistency?
If B is within that, then it's consistent.
So it's precisely the right-hand side,
Oh yeah, the X.
B's, for which the system of equations Ax equals B is consistent. So when you wrote out constraint equations for Ax equals B to be consistent, you were giving equations like we had here, 3b1 plus b2 minus 5b3 equals 0. Those were equations that had to hold for these b's. So what does it mean then if we're saying that we get those equations from the left null space?
That the B's are.
Three B1 plus B2 plus, yeah. So B dot, yeah.
Finish the sentence.
W is in the null space of the A transpose.
You all agree with that sentence? The vectors in here are coming from these rows, which is saying that B has to be orthogonal to these vectors. That's what those constraint equations are. When you write down 3b1 plus b2 minus 5b3 is 0, you're saying this vector dotted with b is 0. So in other words, what are we saying here?
Column spaces.
The column spaces are orthogonal.
There's something with perps going on here, isn't it?
Column space perp is left null space. What I'm
Well,
Yeah.
left null space perp.
certainly any vector in here is orthogonal to all the columns. Because this is the set of b's we just said. We said the column space is the set of b's for which it's consistent, and any vector in here is orthogonal to all those b's. That's what we just said. But in fact,
And every B within C of A is within the null space per.
say again?
And then you can show that column space is within left null
Yeah,
space.
is that obvious?
Because the B's have to satisfy
Oh, I see.
the equation.
You're saying if I take any vector in the columns that's in the span of the columns, it has to be orthogonal to these vectors that give the constraint equations. So you're suggesting now that these are actually the same subspace. I was going to do it in a sneakier way, using what we just did about dimension. Remember we said if you had two subspaces and one was contained in the other, remember we had if W is a subspace of V and the dimensions are the same, then what has to be true?
The V is,
And they have to be the same. So let's now go back to our discussion of dimensions for a minute. What is so we stated this all the other day, but we now write it down. What are the dimensions of our subspaces?
Number of vectors in the bases.
So for number of vectors in a basis. So what about the row space? What did we say?
R,
How many, what's a basis for the row space?
rank,
Number, yeah, right.
R, it's the.
Basis for the row space. Non-zero
Rows.
rows of the echelon form. How many rows are non-zero?
R.
Rank. That's the definition of rank. Now, what's the dimension of the column space?
R as well.
It's the same because you have.
No,
vectors
it's
and you
number of
pivot.
pivots, so, right?
Number of pivots, right? Because we've got one column for each pivot.
Yeah.
Number of pivots is rank again. Right, number of pivots in echelon form is rank. What about null space of A?
N minus R.
N minus R, because we got one vector for each free variable, and number of free variables plus number of pivots is the number of variables altogether. And then by complete analogy with that,
N minus R.
M.
so this was the number of columns minus the rank.
it's gonna be the number of.
Well, now when you transpose, what's the number of columns?
Number of rows, so it's M minus R.
And then still the rank's the same. The rank doesn't depend whether you have row space or column space. This is the column space of the transpose, still has the same dimension. All right, so I now want to finally nail down something that we were talking about back in chapter 1. Suppose, so let's actually state this as a proposition, just so you pay attention to it. Suppose V is a subspace of Rn. No infinite dimensional things to worry about here. What's the dimension of V perp?
N minus dimension.
So we observed this casually without knowing what dimension meant,
Right.
but
Plain.
certainly in the situations where we could draw pictures, if that was V, and we drew a picture of what we thought V perp should be, it sure seemed like the number of basis vectors here plus the number of basis vectors here ought to add up to the number of basis vectors in Rn. Does this remind you of something you're doing for homework right now? Some of you have already showed me papers where you were working on it.
Which problem?
The U plus V
Yeah.
problem.
Oh, yeah, I know.
So intuitively, it seems like any vector in Rn should be able to be written as a vector in V plus a vector in V perp. We're going to talk more about that in terms of projections next chapter. But if you paid attention to your homework, projections are already showing up. So it shouldn't come as a huge surprise that it's going to come in more later. But let's give a proof of this without just saying, oh, it looks obvious from a picture. I mean, that's not a good argument. Hint, I want you to set it up so you can use all this stuff we've done over here for matrices. How can we relate this stuff to matrices? Well, what is the relationship between, this is like what I was doing earlier, how are row space of A and null space of A related?
Perps to each other.
Well, let's see. When you multiply A by X, you're saying that the dot products of the rows of A with X are whatever your answer is. So if the answer is 0, you're saying that the dot product of the rows of A with X are 0. This is similar to what I was saying up there. So if X is in the null space, then that means X is orthogonal to any of the rows of A. Which means it's orthogonal to any linear combination of the rows of A. So what does that mean? It's in what?
Perp space.
Perp. It's orthogonal to any linear combination of the rows of A. You okay? Go get water if you need some. All right, so you're orthogonal to all the rows of A, which means you're in the orthogonal complement of the rows of the row space. So what does this mean? It means that the null space is contained in the row space perp. But in fact, is the row space in the perp of the null space?
Sure. Nice guess. Yes, they're gonna be perpendicular to each other. Yes.
Well, how do we see that? Don't you in fact have equality here?
Yeah.
Because if you're in the perp of the row space, that means that you're orthogonal to all the rows, but that's exactly what this says. So on the other hand, the row space perp is certainly in the null space, because if I take any x whose dot with all of the rows is 0, that means it satisfies this equation. So really this was all if and only if.
Yeah. Okay.
Right? Isn't that what we should have said in the first place? So let's erase that. All right. So do you think you can use this to do this?
Sure.
No.
No.
Wait, use what to what?
Use this observation to prove this in general.
Could you say that? Say that V.
If I take any subspace,
Could you take a basis for the subspace, make it the rows of the matrix?
very good. So the proof of the proposition, choose vectors v1 to vk that give a basis of your subspace. Nick says make them the rows. So here's my A, and I put my vectors in sideways. Well, what do we know? What's the row space by construction? The row space of A is what?
V.
V. So by what we just observed, what do we know about the perp?
It's a null space.
It's the null space of A. And in fact, if you wanted to find the perp, if I gave you numerical vectors, you might very well find the perp by exactly finding the null space of this matrix. So we'll do an example in a minute after I finish the proof. Okay, so by construction, the perp of the row space is the null space of A, but what about dimensions now? What's the dimension of the null space? N minus R, and R is the dimension of V, because these were all linearly independent vectors, so the rank is K. So here, in this case, K, which is the number of vectors I have, to give me a basis for V, and N minus K is the dimension of the null space, which is V perp. So that's this. Okay, so let me just finish up this thought before, and then I'm going to do some numerical examples here. Corollary. When V is a subspace of Rn, V perp perp is V. You will recall from chapter 1,
We did that for
no, you didn't do this.
We
We
thought about it.
Considered it.
What did you do in chapter 1? You proved
that it's
That-
contained in.
Yeah.
You proved that V is contained in V per perp. You showed that any vector in V was orthogonal to all the vectors that are orthogonal to all of V.
Yeah.
But, and I asked you, do you think more is true? And you all said sure, because you drew pictures and you looked at them and you said,
It must be equal.
they must be equal. And I said, well, coming soon will be an example as a challenge problem where they're not the same. We're not quite there yet, but soon we will be. But now, why are we done? If you have a subspace of if you have two subspaces,
Their dimensions are
and their dimension. So what's the dimension in this case? What's the dimension of V perp perp?
V. The dimension of V.
Is
Well,
N
by what we just
minus
proved,
N
N
minus
minus dim V.
it's N minus dimension of V perp.
which is N
Just N
minus
minus
N minus plus dv.
And the dimension of V perp is N minus dim V. And by
So it's just
distributing
Dimension of
multiplication by -1 or subtraction or something,
dimension of V.
they have the same dimension. So if you have two subspaces, one contains the other, and they have the same dimension. So I told you we'd use that. So what does this mean? It means that I can go around perping to my heart's delight and I know it's all correct. So it follows that we have just established now that the perp of the row space is the null space. I can now perp both sides.
Yeah.
You knew that perp was a noun, but you didn't know it was a verb. You can now perp both sides and use the fact that row space perp perp is row space. And now if you replace A with A transpose, you get row space of A transpose, that's called column space, is the null space, perp of the column space is the null space of A transpose. I think we were talking about that earlier. And then perping again, the column space is the perp of the left null space. So this is good because otherwise I could never remember which one was true and which one was false. I would never remember where the perp went and where it didn't go if I couldn't put them everywhere. It's just important to remember, as I drew you the picture the other day, that you have two of these subspaces going on in Rn and two of them going on in Rm. So you've got the row space here, you've got the column space here, but they have the same dimensions. And then you've got the perp here, which is the null space. And then you've got the perp here, which is the, oh, that didn't look too perp. Doesn't look too good either. Perp. Can't catch your tongue? Oh well.
Those dimensions are not the same.
And those dimensions are not the same. So if I hand you on the next exam or web work a subspace and I ask you for its perp, how are you going to do the problem? Say I ask you to find a basis of the perp. What are you going to do?
First, you put it in matrix.
So, well, what some of you have done in the past is you've thought about it in terms of columns. So what I want you to do when you're working these problems, and I will take off points if you don't write some words, Dan. I want you to make a matrix. You can pick whether you want these to go in as columns or as rows. But you've got to explain to me what you're doing. So method 1, create an A so that the subspace is the row space of the matrix A. Then the perp will be
Null space.
the null space. Okay? what would method 2 be?
Create A so that equals the column space.
Suppose you stuck them in as columns. Create, I'll call it a new matrix so we don't get confused, B, so that V is the column space of B. Then what's the perp?
Left null space.
Left null space of B transpose. How are A and B related? Whoa.
They're
So you-
transpose.
The same way we did this thing over here.
So there's my A. I stuck the vectors in as rows. Here's B. You told me stick the vectors in as columns.
It's the same thing.
Well, I think these are related to one another.
It's the same thing as the general case.
It's this thing over here, you just take it over here.
Easy.
It's
B is A transpose. So what is the null space of B transpose?
Throw spaces.
No space is the same.
So you're back to doing, you're really solving the problem the same way. Except, how would you find the perp when you're thinking of column spaces?
Linear combination.
You would you'd think of the column space as the set of vectors for which the system of equations is consistent, and you would put your B's here. And you would find constraint equations. Right? That's how we're thinking about these guys. What would you do here to find?
The non-zero rows.
You just,
Oh.
how do I find the null space of this matrix?
Find any solutions.
So I want to find the general solutions of the homogeneous equation, so I have to put this guy in echelon form, and notice how conveniently I chose the vectors for us.
How can we?
What happens to the third row?
It's gone.
Just,
Nothing.
it disappears, just gone. When you add it together.
These two rows added up to that one, that's how I made this up. So when I do my row operations, I do end up with a row of zeros, and I'm already in reduced echelon form.
How convenient.
So
So -2.
basis for the null space, which is therefore a basis for perp, is going to be -2, 1, 1, 0, -3, -1, 0, 1. Have you guys all caught on to the shortcut without writing out all the equations? No?
Just take that negative.
This is saying x1 is -2x3 minus 3x4. -2, -3. So all the x3 stuff goes here. So all the stuff from this column is what's going in here. All the stuff from this column is what's going on here. And then you've got the x4 pivot variable there and the x3 pivot variable here. I encourage you, just to make sure you don't screw it up, write out the steps and make sure you're doing it right. But that's what's going on there. What do I do here? Well, I reduce to echelon form and get constraints equations conveniently.
Wait, you need another.
Oops. Well, we knew this column didn't matter. Come on.
You just wrote.
Forward and right.
Nothing is different.
Being distracted by the noise. So what happens on this row?
It's gonna go away.
0, -1, -1.
B B3 minus B1.
Yeah.
Minus 2B1.
It's just that
See,
big.
even you have.
Yeah.
Bottom row.
0, 1, 1.
Mine.
One.
B4 minus 3B1.
And now we see that these are going to turn into rows of zeros, as we expected. And what are the constraint equations?
B3 minus 2B1 plus B2. B4 minus 3B1 minus B2.
It's almost like it's shockingly like that.
So what vectors do we get?
Negative 2, 1, 3.
So we found constraint equations for this system of equations to be consistent. Remember, that means that the coefficients of these equations are giving you the normal vectors to the subspace. So what are we getting?
The
Negative 2,
1,
1,
1,
3.
1, 0,
-3,
negative 3, negative 1, 0, 1. Looks familiar, doesn't it?
Oh,
that was a lot shocking. Whoa.
Well, not so surprised. What is a little surprising is that you got the identical vectors.
yeah.
You're not surprised that you got
Same.
the same subspaces because that was obvious. But in fact, the algorithms give you the exact same vectors.
We did that one in like the third.
This was easier, right?
Yeah.
Especially it's easier not to make mistakes doing those things.
So since you called me out on my verbosity, so if I just write that one line there, then I'm good?
Yeah, so what I'm asking you to do to stop you from making mistakes, it's all in your best interest, is to say how you're approaching the problem,
Right.
and then write down the relevant result from there, and then proceed. What I've seen a lot of people do is put them in one way and then not do what they were supposed to do.
Right.
All right, so you can also, do I want to say more about this? So if I could phrase this a different way, I could ask you, rather than saying find the basis of the perp, I could hypothetically ask you for a system of equations that A satisfies, that B satisfies. So I'm back to what's going to be a major theme that I'll start discussing tomorrow. When you say V is the span of a bunch of things, you're representing V in explicit form. You're basically saying any vector in V is a linear combination of these vectors. But now if I ask you, express V as a solution set of a system of homogeneous linear equations, I'm now asking you to represent V as a set of solutions to equations that's implicit. Now, how would you actually do this? Suppose I hadn't asked you what V perp was, what would you do to do this?
Put in.
How would you say,
Dot those with x equals 0.
dot whom?
The basis.
Yes, so in other words, the answer would be, to the problem that we just did, any vector in my original subspace has to satisfy these two equations. I have it wrong? No. Right, you're saying any vector in V is orthogonal to both of these, and only the vectors in V are orthogonal to both of these. So what are we using here? to make this deduction. We're getting V as the set of vectors x
V per.
that are orthogonal to whom?
V per.
So V
Per.
is the perp of V perp. That's where we're getting these equations from. So even though you thought this was silly, it conceptually means that you can start with an explicit representation and create an implicit one. By finding perp of V, you can now give equations for V, namely it's the set of all vectors that are orthogonal to all the vectors in V perp. So this is actually important. Conversely, if you started with a system of linear equations, how do we write V explicitly? So I just talked about how we're going this way. How would you go the other way? You start with AX equals 0. How do you give a basis for the solutions? Just the general solution of the homogeneous system, right? That's what we've been doing. That's what we've been doing for weeks now. Okay, I want to close with one more comment here. We said that the row space and the column space were the same dimension there. I want to draw you a picture here. Think about solving AX equals B when B is in the column space. In other words, when the system is consistent. So in this picture that I was drawing up there, you take a B that's here. And back here, how do I write down what the solutions look like? Well, if B were 0, I would have the what? The null space. What happens as I vary B?
You're translating.
I'm translating that subspace. So do you remember we talked about how you could take any solution of AX equals B and add all the solutions of the homogeneous equation to it, and you would get other solutions. You take any solution of AX equals B and you add a solution of the homogeneous, you get another solution of the inhomogeneous. So exactly as Mallory said, you get the solutions of AX equals B by translating the null space, and that's what our algorithm does for us when we write the general solution. But back in this picture is the row space. And the row space is orthogonal to the null space. So this line is going to intersect this plane at a unique point. So there's a unique vector in the row space that maps over to B. So there is a one-to-one correspondence. You take any vector B in the column space, and I find you the solution of AX equals B that's the shortest vector, and that's the vector in the row space. Among all the solutions in this orange plane, this guy is the shortest vector. Okay, so I'll pick up and talk about this a little bit more tomorrow, and then we're on to section 5. So come in with questions if you have questions on this stuff.